I need to tell you how to compute the Jacobian. I told you we had the stability matrix, or the rate of shear, but we want to find the finite time shear, which is given by the Jacobian. So how do we do it? There are two ways to do it. One is to write the differential equation. What's the rate of change dx at time t? By the way, you're very quiet, and I really appreciate it. I'm not being interrupted, but you can ask me something if you want. Initial condition, it doesn't depend on time, multiplied by this matrix, which is time dependent. So what is this thing? So there are probably simpler ways to argue it, but you can think of this time derivative for every matrix element as what it is, time dt later over time t divided by delta tau, and then we'll take the limit, multiplied by delta x0. On this side, it's delta x at time t plus delta t minus delta x at time t divided by delta t. So I just rewritten this Newton-Leibniz-like. But this one I can do a Taylor series. So I can write this as 1 over delta t times, and when I expand the first term, we cancel, so that'll be term proportional delta t, so I'll find delta x, delta ith component, times delta x dx dt times delta t. So this guy cancels, and out of it comes a very simple equation which says that this is true for any initial x0. So I get dj at time t, delta t, is proportional to this matrix. And if you believe this, you'll believe anything, but you find out that variation of this matrix J is actually given by the matrix of velocity gradients. So the way this instantaneous distortion rate shows up, it shows up in the instantaneous change of the Jacobian. And it's a linear equation. It depends on where you're on your trajectory. And now you can just put this on your computer and compute at the same go the thing that you, for example, did for a flare. So you integrate this equation in 3 dimensions, d dt. And then you have d dt for every component of the Jacobian. You have the equation gij, which is you multiply by this matrix evaluated at this place on the trajectory, having started at x0. And the initial condition is, at the initial instant, there is no distortion, so there is just 1. When I started the system at initial time, nothing happens. So that's d square equations. And for your slave flow, you can do it, because there'll be 3 plus 9, 12 equations, and your Mathematica or whatever you're using can handle probably 1,000 or something without thinking very much. That's it. So if I was of certain school of thought, I would now say mission accomplished. This is a linear equation. This is usually totally innocent. This stability matrix is usually something that has finite elements in it, because you have some vector field and velocity doesn't go to infinity, and it's not allowed to go to 0, because if it goes to 0, then you stop, then you're solving a different problem, you're at equilibrium. So this is kind of normal, but this is a linear equation. So these elements which are normal will get exponentiated, because linear equation in a way that requires some thought, jt is really just an integral of whatever is here. So it's, it's something like that. So, what I'm writing is not correct, but it's morally correct. It says that even though this matrix here of shears instantaneous shears is a bunch of reasonable numbers. T can be anything. So the elements of this matrix can get very big, arbitrarily big as time goes. They're all growing exponentially. Now, some of them are getting exponentially big. So the leading multiplier is maybe 10 to 103. But other ones are getting exponentially small. So the smallest multiplier is 10 to the minus 214. So suddenly your matrix, you need 300 digits of accuracy just to get one digit of accuracy on slowest eigenvalue, because you're computing at the same time very huge and very small numbers. So it turns out nothing has been accomplished by writing this. The thinking only starts now. How do you compute it? Oh, that one. That one is criminal. But you guys believe anything, so who am I?
KJ.
Yeah. I can write anything I want. I mean, you'll be just... Actually, now I'm seeing many more videos that I ever wanted to see in my life, and so YouTube opens this stuff, and one of them is video below my video said English teacher discovers that he can tell the kids anything.